Okay, good afternoon, everyone. I would like to welcome you to the public defense of the PhD thesis by Marcel Bernet with supervisors Teresa Antoya, Constantort, and Pau Ramos on data-driven diagnosis of the Milky Way dynamics. I'm the chair of the examination panel. I'm Mina Hermi from the University of Groningen. In the Netherlands, we have Francesca Figueras as the secretary of the panel, University of Barcelona, that you all know, and Jason Hunt, who's lecturer at the University of Surrey. So without further ado, you have about 50 minutes up to, and then we go on to questions.
Thanks. Okay, so before starting, I just wanted to say that I prepared this website to follow. This is going to be a fairly technical talk and in English, and I prepared this for friends and family to follow the presentations. You will find keywords here. If you introduce them, it will pop up and tell you things. Okay, so imagine that I have a river here in front of me, and imagine that I have this amazing tool that allows me to measure for every particle of water right in front of me its position and its velocity. If the river is ideal, if there is nothing happening there, all the velocities of the particles will point all to the same direction. Yeah. But now imagine that I move here and I put a rock. Now the particles need to avoid this rock, and when I get back here, all these velocities will not point to the same direction, they will point to different directions. So one could think that if we have this information measured, we can use these velocities of the particles next to us to infer the shape and the distance to this rock. So that's what we do in galactic dynamics. Now, of course, our particles are not water particles, they are stars. And with Gaia, we can measure their position and their velocities with a lot of precision. So what we do in our field is using these positions and velocities of stars to try to infer the shape and the history of the rocks of our galaxy. So I introduced two things. First the instrument and then the rocks. As for the instrument, we're using data from the Gaia satellite. Gaia is a mission from the European Space Agency, and during these last 11 years, it's been observing about 70 million observations per day. And from all the Gaia data, the catalog we are interested and the one we will use during this thesis is Gaia DR3. Gaia DR3 provides about 1.5 billion information, astrometric and photometric information for this large data set. But from this 1.5 billion, we're interested in these 33 million stars that also have velocity, radial velocities. For this subset, we say that we have 6D information, 3D positions and 3D velocities. And I wanted to mention that I've been especially involved with the Gaia data. I started working here in this institute as a software developer in 2019 with the Gaia UV team that are present here. And during this thesis, I've still been involved with helping the core processing unit of Gaia, Deepak. So it's been a nice journey. And now, if we take this 6D velocity sample and then project it with different combinations of parameters, I will explain with more detail this graphic later, but I was just going to give information that when we project this Gaia data, we observe all these overdensities and underdensities and things that are happening, and these are exactly the projections of the rocks that we want to study. So every rock will produce one of these features here, and our goal is to study what's their meaning and their origin. Now, going to what are these rocks that I was mentioning, we know that in the disk of our galaxy we have a bar and we have spiral arms. Surrounding our galaxy we have this dark matter halo, and if we zoom a bit out, we have satellites. And now to describe them a bit slower, I will start with the galactic bar. Galactic bar is a large-scale, non-axisymmetric feature that influences the evolution of the disks of galaxies mainly through what we call resonances. And what's a resonance? A resonance occurs when the frequency at which a star is orbiting the galaxy matches somehow the frequency at which the bar rotates. If they match, this extra force, that periodic force that appears, can distort the orbit of the star. There are a bunch of different resonances, but I will explain the two main ones that we will use in this talk. The first one is corrotation. Corrotation occurs when the particles are rotating at the same speed as the bar. Actually, here what I'm showing are orbits vibrating around corrotation, but yeah, that's the point. And the other main resonance that we mentioned is the outer Dirac resonance. This happens when, for each azimuthal loop of the star around the bar, it does two radial oscillations. And why are we interested in these resonances? Because whenever we have a resonance on the galaxy, what these resonances do is to trap stars in a given position of the phase space or scatter them. So when there is a resonance, what this does is create voids and overdensities in the phase space. And that's exactly what we are looking for in the data, these voids and overdensities. So resonance can be one of the mechanisms that produce these voids and overdensities, not the only one, but that's just to explain why we are interested in resonances. The second rock that we will study are spiral arms. Spiral arms are these big features that we can observe in external galaxies. They are ubiquitous, they appear everywhere, but their nature is not clear yet. We have some competing but non-exclusive mechanisms that could produce these spiral arms. And in addition, studying them in the Milky Way it's an observational challenge because it's very difficult to locate them and to say precisely where they are. And again, spiral arms influence the evolution of our disk through resonances, the same way as the bar, but also due to enforcing star formation, radial migration, and other phenomena. Okay, going to the last rock I want to introduce, we have these satellites. The main two perturbers that are interacting with the Milky Way right now are Sagittarius, which is this dwarf galaxy that has about 1/25 of the mass of the Milky Way, and it has been interacting with the galaxy for the last 5 years. And the other one is the LMC. The LMC is larger, it's about 1/10 of the mass of the Milky Way, but we think it's on its first infall, so it's just starting to perturb our galaxy. And how will we use all this information? All these rocks, bars, spiral arms, satellites, the shape of the dark matter halo, what they condition is the galactic potential of our galaxy, so how the forces of the galaxy are distributed. But we cannot observe this, or it's very difficult to observe it directly. But what this potential does is to govern the orbits, so how will stars move through this potential. And that's what Gaia can observe. That's what we call the river flow. So our goal in this thesis, and the goal of our field, to which this thesis tries to contribute somehow, is to infer the dynamical mechanisms that have shaped our galaxy through the study of the Gaia observations. I will drink some water now and stop here for a dramatic pause. Okay, so this thesis is structured in 4 different articles. In the first 2 articles, what we do is use the Gaia data to try to constrain the properties of the galactic bar. In the third article, we studied how the spiral arms of a galaxy interact with the dark matter halo and what consequences could this have. And in the last article, we study one type of spiral arms that appear after the impact of a galaxy with a satellite. So these are the three rock river mechanisms that we will study. Starting with the first one, I promised that I would explain what this is. So that's what we are going to do now, build this diagram and use it to constrain the parameters of the bar. So let's start by taking a very small region of stars very close to the sun. For each one of these stars we can compute its radial velocity outside of the galaxy and its azimuthal velocity around the galaxy. We will take this information and plot each star according to their velocity in this diagram, and we obtain this image. The nice thing of this image is that if you see there are different arches and voids and overdensities and underdensities, and each one of these features is giving us information of these rocks of the galaxy. So our goal will be trying to distinguish different overdensities and trying to explain the mechanism that form each one of them. I will focus on the next slide only on this large void here and forget part of the rest of the structures. When focusing on that void, there's one possibility of explaining this overdensity, that is that the bar is rotating at a given pattern speed, so at a given frequency, and this locates the outer limit resonance in this position of the phase space, and produces these two overdensities, one in the bottom and one in the top. But there's another possibility that if the bar is rotating a bit slower, instead of the outer limit resonance, co-rotation puts also an overdensity in this region of the phase space. Which means that for one single overdensity, we have two competing mechanisms that provide the same answer. And we call this a degenerated space, where two different ways to get the model give the same response. So the way we try, the first step to try to solve these degenerations is trying to understand to understand well how is the data and what are we observing. I forgot to say that not only there's this mechanism, but we can include different shapes of bars, spiral arms, and combinations, and there are a lot of different ways that we can combine and find good matches between models and observations. So it's a very broad parameter space for a limited amount of data that we want to fit. And I'm happy to be here explaining that because in this group, in my group, our group, we have a long tradition of studying exactly this space and trying to understand it well in order to fit them to models. Back in 2008 and previously in 1998, Tesla used the Geneva-Copenhagen survey to study this space using the wavelet transform. And then in 2018, when we had the Gaia DR2 data, Pau in his thesis did this famous figure where he studied the thin arches that form the distribution that we were talking about. The nice thing of that article is that he could move around the disk. So what they did is repeat this exact analysis, but moving in different regions of the disk. And then what you can do is try to link one of these arches, how it appears along the Milky Way disk. So that was a very good result and had a lot of new ideas and very good art detection and the first detection for this large scale structure, but that it had a key limitation. That was that this linking of structures need to be done visually. So by hand trying to link all these dots. So that's where my thesis started, and the first idea, the idea we wanted to do was to try to generalize that result and do it in an automatic way. So the first challenge was detecting these moving groups, so these overdensities, consistently in each neighborhood of the galaxy. And we did that, again, using the wavelet transform, because that's what we do in our group, and apart from a lot of other nice things. And then we were able to link all of these overdensities. And you can see visually that there's a continuity. No, these points here, they should be linked somehow once with each other. So that was the second task, trying to link these structures in the 3D space. And we did that using a breadth-first search algorithm, a modification of it, that it's an algorithm for graph theory. And using this algorithm, we were able to do a very precise and robust linking of these structures in the entire disk. Not only one direction, but also not only in the right direction, but also in the azimuthal and the vertical direction. So yeah, it was a huge success. And on that paper, we applied, in the first paper, we applied methodology to the Gaia EDR3 data, also in a pair of simulations with a bar. We were able to see that this resonance structure is very complex. These arches join and break and do several complex things along the space of the galaxy. And we are also able to see that these lines here do not follow what you would naively expect for lines of constant angular momentum or constant energy. So that's what Article 1 left us. And then we jumped to Article 2, where the goals were continuing the project, so applying the same methodology, but now applied to the Gaia DF3 data, which was a larger data set with better quality. And the goal was trying to fit a bar model not only to the local space, as I showed at the beginning, but using all these large-scale results to fit the bar model. And finally, we wanted to study the degeneracies in the parameter space between the two bar models, trying to find one parameter that disentangle between them. So that's what we did, and we ran this methodology to this new data, and we take these large-scale structures. And the first thing we noticed on this diagram is that this is very linear. So this is a line that covers from about 60 degrees of the phase space. That's okay, it can happen. The only problem, I wouldn't say problem, the only thing is that whenever you see a resonance structure, this resonance structure needs to open and close. So it needs to do a region, and so at some point it needs to go up and then down and then up. So what we point is that either we are in a very specific part of the disk where this is just this part of the resonance, or there are other mechanisms that could be playing a role. At the moment, we don't have enough data to answer this. We just point that with using Gaia 4 or new surveys, we could, it's a way, we are pointing to where to look with this new data. Especially because we are reaching already what we think is the tip of the bar, where in a resonance picture, things should change their trends. Okay, so now we have this huge data set of structures around the disk with all these informations, but we want to find a way to visualize them and understand, visualize the global picture in a way that humans can, we humans can see. So what we did was take every one of these structures and compute their gradient. And now what I'm doing is coloring. Orange and red will mean the structures that are more steep, so go down faster, and green will mean structures that are slightly flatter. So we compute this for each structure, and we get this kind of diagrams. This is the same diagram as I was showing before, but now this yellow here is telling us that this structure is steeper, and this green is telling us that the structure is flat. So what we are doing is taking this global information and compressing it to a local space. And with that we are ready, because what we have is this very good quantification of the data, and what we want now is to compare it with galactic bar models to try to do this fit. So we have the data we want to compare. What we did is using backward integration simulations that allow us to do very fast calculations of this local phase space. And when we did that, we take our data and we compare it with a slow bar model. We were able to get with high precision the position of these over densities, but we expect that because that's what the papers of the 2000 were doing, fitting the position, but our goal was trying to fit these gradients, fit the colors. And we see that with our models, this was not possible. There is this 3 sigma difference between the radial gradient that we observe in the data and the radial gradient we get from the simulations. This is for the slow bar model. For the fast bar model, this difference is even higher. We computed about 6 million different combinations of parameters. Those were models with different bar slope and pattern speed trying to do this fitting. And not only we did it in the radial direction, but we also did it in the azimuthal direction, and the details of this process are on the thesis. And with that, we concluded that simple bar models do fail to reproduce these measure gradients without this 3 sigma tension for the Hercules moving group. And this is kind of expected because the consensus right now is pointing that the Milky Way bar is slowing down, and this could indeed change the shape of the structures. So in the paper we point to different possibilities, different bar potentials, spiral arm, complex irregular velocity curve, perturbation. So there are a bunch of different ways. What we did was discarding this simple bar scenario. And in general, to conclude this first part, we have this really good method that provides this 6D map of the moving groups. This skeleton of the phase space of the Milky Way that we are producing is very suited for quantitative comparison between the data and any n-body model or test particle model that you could throw in. This has already been used by Yasin Khalil and he ran the method in a simulation. Also, Lorenzo Spina used our linking of the moving groups to compare with some halo population results. So it's already in use, and this method is by definition n-dimensional. So it's suited to add any extra dimensions you could think of. For instance, we could include chemistry, age, or any variable. So that's it for part 1, and now we'll jump to the second part of the thesis. And here we change our picture a little bit, and we'll study how the spiral arms interact with the dark matter halo. And I think the best way to introduce this part is just explaining how this project came up. We were in a room discussing, analyzing this simulation. This is an isolated pure MOD simulation that develops a bar and some spiral arms, and that's it. But one thing that we know about simulations and bars is that they slow down, as I was saying before. So if you observe this bar here in time, it first rotates fast and then it slows down in time. This is one example of this slowing down. The mechanism that slows this bar down is what we call dynamical friction. It's basically the friction between the bar movement and the dark matter halo around it. And one curious thing about this dynamical friction is that when you take the dark matter halo around the bar and observe it, you see that this bar-like overdensity appears in the halo that we call a shadow bar. It's the response of the halo to the movement of the bar. So we were in that room discussing this phenomena, and I asked the question of, okay, if bars move in a dark matter halo, they produce a shadow bar. When spirals move in a dark matter halo, do they produce shadow spirals? So that was the question I threw, and then the next step was let's go to the literature and see if anyone has thought about this previously and what were their conclusions. We saw that back in the 70s and then in the year 2000, using shearing sheet formalism, so pen and paper, Mark and Fax and Tadasula predicted that this coupling between the spiral arms and the dark matter halo would produce an enhancement of the growth of the spiral by a factor of 2. But then the other paper that mentioned this coupling was a paper by Selwood in 2021 that tested with simulation with a fixed halo and a live halo, and he saw that there was no significant difference in this growth. So we basically detected that this was an understood phenomenon. There were 3 papers mentioning it, and it had several potential implications on the structural dark matter around us. So it was an interesting project to study. So we went back to the same simulation, took these are the stars of the simulation, and here what we are doing is taking this same sample and removing at each radius, so at each ring of this simulation, we are removing the mean density. That way we enhance the spiral arms. No? If here in red there's this overdensity, that corresponds to this overdensity here, but it's seen with more clarity. If we take this same method and repeat it on the dark matter halo, what we see are these red blobs that are the dark matter spiral arms we were thinking before. So yeah, we see them. We went afterwards to a lot of different simulations, a pure embodied simulation with a satellite passing. We also saw these dark matter spirals. We went to isolated hydrodynamical simulations. We also saw spiral arms. We went to Auriga cosmological simulations. Again, they were there. So it seemed like a fairly common phenomena in any simulation that we observed. And then next step was trying to give some more details about the properties of these spirals. As for the mass, we in general computed that this dark matter spiral arms has about 10% of the stellar mass of the stellar spiral arms. They rotate with the same pattern speed as the stellar spiral arms, so they are they have the same frequency of rotation. And in terms of the angle, they are always lagging behind the rotation of the spiral arm. So every time we have this spiral arm, about 10 degrees behind it, we have the shallow spiral trailing. The next thing we did was studying their motion. This is the motion of the stars, and they have this signature of how they move. And when watching the motion of the dark matter halo, we see that there is also a spiral arm signal in the motion map. We saw positive planar motion on top of the spirals and a vertical bleeding motion on the vertical component. And then, after all this analysis, we wanted to give some explanation or intuition about what was the mechanism that was creating those spirals. And our theory was that they were basically a forced response of the halo to a changing potential. So locally, there's this spiral potential passing the halos around, so it has to respond somehow to the change of the potential, and it adapts. The other possible way is that it's a self-gravitating mode. So the halo itself is doing some kind of spiral arm structure just as a disk. The way we thought about to split these hypotheses was doing a simulation that had no self-gravity. And that's what we did. We did this test particle simulation where we have a halo sample of orbits, then we put this spiral arm potential on the middle oscillating, and we recover the same signature. This in black and white is the analytical potential of the spiral arms, and we see on top this dark matter overdensity lagging behind the movement of stars. And in the velocity space, we see the same signatures as before. Positive planar velocities and a breathing motion in the vertical. So we were able to reproduce the same kind of signatures in our model without self-gravity. And the last experiment we did, or thing we did, was, okay, now is this spiral arm response the same for every kind of dark matter halo population? So we split the dark matter particles according to their orbit around the disk. Here, this beta parameter is the angle between the disk orbit and the orbit of the dark matter particle. If beta is 1, it means that they are in the same plane, so the dark matter orbit is rotating in the same direction of the disk. This is the yellow arrow. If it's 0, cosine beta is 0, it means that the orbits are perpendicular, and if beta is -1, it means that they are counter-rotating in the same plane but rotating in another direction. And that told us that for dark matter particles that are rotating in the same direction as the disk, we see a much larger response. This is logical because a particle that is rotating the same direction as the disk will feel this spiral arm potential for longer. But still, for counter-rotating particles, we see some signature there. So that's an interesting thing. Yeah. Sorry. So we conclude that these dark matter spiral arms are but were predicted theoretically. We can observe them in any kind of simulation that we looked at that had enough resolution, and we conclude that they must exist in nature. So whenever we observe stellar spiral arms around, we should expect this 10% increase on their total mass due to this coupling, this response, and just hinting that this is a fairly that it's structure that it's fairly close to the sun, so it's giving us some kind of dark matter substructure close to us, and this could have some implications both in dark matter direct detection and dark matter nature studies that we could test somehow. And in general, the influence of this coupling in the evolution of the stellar arms itself, it's an understudied topic, so it's a very good opportunity out there to continue this research. And just as a side note, this article did take some repercussion on outreach. There was this outreach paper, and then it got some mirroring on the Nature Astronomy and even in the Kazakhstan news agency. So that that was a nice experience. Okay, another traumatic pause to drink water. Okay, now that we turn to the last part of the talk, this is the fourth article, and here what we will use the Gaia data to measure to try to understand one special kind of spiral arms that occur after an impact, satellite impacts our galaxy. To start, why are we studying this? We know that the Milky Way disk is currently being perturbed by satellites. There are several different evidences pointing or hinting this possibility, and others, but like the common way. Okay, yeah. First is the vertical phase spiral, then the reflex motion of the disk through the movement of the LMC, and we have finally the work, and there are other evidences of that. And the simplest way we can simulate one impact of a satellite to a galaxy is with what we call the distant and impulsive approximation. Distant means that we assume that the perturber is very far away. Impulsive means that we assume that it goes very fast. So we are doing this simulation with t time equals 0 instantly. The nice thing about this approximation is that then you don't need to simulate the full orbit to have the initial conditions. You just need to apply what we call a velocity kick. So a change on the direction of the velocity of the particles, and with that you are done. So we start with this very simple setup, and then when we evolve it, we see this double spiral appear. We see this long wave spiral in red and blue, and then we have a short wave spiral on top of it. On top of the blue spiral here is where we expect density increase of the stars. And the way we got interested in this project in this thesis is because back in 2022, we did this project with Teresa where our goal was to use these same kind of simulations to try to find how a galaxy after this impact would look in the phase space. So we were trying to compare the phase space of these kind of impacts with the Gaia data. And one thing that we were able to do was to give closed analytical expressions for these dashed lines, so the locus of the spirals. And this locus was able to measure some parts of the curvatures, some changes of trends of the curvatures, but one of the paths of the paper where we got stuck was when we would try to fit an analytical equation to the entire curve. So there's this sawtooth pattern that appeared in BFI and this triangular wave that appeared in BR that we were not able to give an analytical expression for these shapes. So that stopped there. The paper was successful in other directions, but that was a leaf of the tree that was stopped there. So then, a few years later, I discovered a method that what it was was a method that you were able to fit some simulations to it, and then in a complex way it returned the governing equations of the system. So I thought, can we apply that kind of methods into this problem to overcome this limitation? So that's what we did. And the method is called SINDI, Sparse Identification of Nonlinear Dynamics. And the way it works is you start by simulating your data. So we had this simulation that I've introduced. In this case are simulations with a very small impact. So the initial perturbation is really small. And then what you do is to what we call build a library. You compute numerically all the terms that you think they could come into the equation. In this case, we compute all the moments of velocities, their azimuthal derivative, their radial derivative, and all the polynomial combinations to second order between them. You fit all of these terms into the method, and what the method tries to do is to solve this linear system, putting as many zeros as it needs. And the outcome of these resolutions, or the coefficients of these resolutions, give you the equations that govern the method. In this case, we used a very simple impulse, very small impulse, and it's a system that is known and solved. So after running SINDI, we obtain the linearized Boltzmann equations that we know that must govern this system. So it was a very nice proof that this kind of approach can indeed lead to good results. These equations are linear, so they can be solved analytically, and the resolution of this equation explains why there's that long wave and the short wave that I explained in the beginning appear. So with that, we can explain this appearance of the long and the short wave. So now we were ready. We could take SINDI, fit in simulations with a larger impact, and try to find this equation that we want that governs this large impact system. So we did that, and before showing the results, I wanted to stress that this is not a trivial method. There are a lot of steps involved in it. It's not magic. You have to numerically compute the spatial and temporal derivatives. That's delicate. You have to determine the library of parameters that you want to fit in, and that's also non-trivial because you have to have some intuitions on the system. And finally, the method always returns an equation, which is a problem because when you obtain an equation, you have to validate somehow independently, both with pen and paper and with physical intuition. You have to validate if the resulting equation makes sense or not. That said, we take the large impact simulations, we put them to SINDI, and we obtain those equations that are this nonlinear system of partial differential equations. And this system of equations was previously unknown, at least in the context of galactic dynamics. It's not a general solution in the sense that this P and Q coefficient depend on the shape of the initial conditions that you put. And very important, this system is known that has no analytical solution. So that this part here explains why back in 22 we were not able to find this analytical expression for the curve. The answer is it doesn't exist. So good for that. Well, so how do the solutions of the system, these equations that allow us to evolve the system, and this in light blue, this is the curve that a very small impact would produce, and it's fairly sinusoidal and symmetric. But then when you have a large impact and you evolve it using this simulation, you do obtain this triangular wave in BR and this sawtooth wave in B5. So yeah, indeed we are, this expression is explaining the shapes that we had at the beginning. And this way of working with the equations directly is nice in the sense that it allows you to do extremely fast simulations and to redo these impact simulations in a very fast way and iterating directly in the momentum velocity space. And the last thing we did to validate this CD method was running this methodology in a more realistic simulation. In this case, this is a full MOD simulation run by Detsuro. And for this simulation, we have this test particle rerun, which is the same setup, but without self-gravity. When we run CD in this setup, we obtain exactly the same nonlinear PDA structure. So in some sense, this was a very nice result because it found the same math, but it found a slightly suboptimal coefficients. And again, that's expected because we are running a method with a library that is designed for things that have no self-gravity and no velocity dispersion, and we are throwing a system that has self-gravity and velocity dispersion, so we expect a suboptimal fitting, but it is pointing to possible improvements we could do on the methodology. By filling it more terms in this library, we could find this extended math to model the system. And without all of that, once we are loaded with our methods and weapons, we can go back to the Gaia data. When you take the Gaia data and plot this LZ versus mean BR curve, it's known that it produces this double wave pattern, this long wave here and the short wave on top. And if I design well this presentation, it should trigger again back to this double spiral pattern. So that's what we wanted to test. We knew at the beginning that when you have this impact, it creates this double spiral pattern. We wanted to test if with that double spiral we can fit the Gaia data. So this wave here, if you extend it in the azimuthal direction, you get this kind of diagrams. And our goal was, can we fit this three-dimensional pattern using a simple impact and the equations we rediscovered? And the way I thought is this: we can simulate very easily an impact using only two parameters, so it's analytic impact. Then we evolve it in time with this linear PDA system that it's also analytic. So we obtain this analytical BR-defined maps, and with that, it's very easy to transform into maps equivalent to this one. So we designed this fitting procedure, we ran it, and what we obtained was this fitting, which is good in some parts, not so good in other parts, but very informing in its globality. It's good in the sense that this fit, as described here, it has analytical parameters, physical parameters. You have the angle of the impact, its mass, and the time since the impact here. So it's giving you physical measurements. For the long wave, we obtain a fairly good fit. This fit gives us physical measurements of the impact we expect. This is in the short range of the Sagittarius time impact window and in the long range of the mass impact. So it's but fairly consistent with the measurements that we get independently, with all the caveats that this can have. But for the short wave, so this pattern here, the fit is very suboptimal. it's about 1/5. This is 1/5 smaller than the one you expect this here. So this again discards this shortwave spiral as the explanation for this shortwave in the data, and points to more complex models, such as a double impact of Sagittarius or the signature of a bar. So that's what we conclude. So yeah, to conclude this third part, we opened this new way of thinking for galactic dynamics. We discovered this new nonlinear system of equations that explain the sawtooth and the triangular wave. And when we applied this model to the Gaia data, we were able to discard a Sagittarius impact as the single explanation for the LZ PR curve. And with that, I reached the conclusions of the paper, of the thesis. When I was this weekend thinking of how to start the conclusions of the thesis, I remembered the first meeting I had with Teresa and Pau back in 2021, I guess, where they explained me that they had this 6-dimensional data set that whenever you project it in different combinations, you could do a lot of science, but we are not able as humans, of course, to understand these 6 dimensions all at once. And for me, as I have mathematician background, so that was like, yes, I need to get involved in this. So that's been kind of the streamline of this thesis, trying to provide tools that help us understand these complex data sets as humans. For the initial plot that I show, the skeleton run, the method that we ran was able to relate these 3 plots using single groups. So they are 5-dimensional groups that reproject in this diagram in this way. This is the first map, 3D map of these moving groups. This is a very high precision quantification of the Gaia physics space and very ready to compare with any simulation or model that we have. And there are several places where this system could be included. We could use it to run in LMC data, to include this age or chemistry and whatever. Following the same reasoning, simulations are an extra dimension. It's taking this 60 space and adding a 7th dimension of time. And simply what it does is trying to do this, taking all this 7-dimensional data and converting into equations that they might seem elfish, but they are really something that you can understand and treat and process in your mind. So yeah, we pioneered the use of this tool for galactic dynamics and opened this possibility to discover new physics. And this approach, we think that it can be fairly easily extended to model self-gravity and to model the vertical planar coupling, and even to apply it to IFU data and external galaxies. And this is a very nice tool for galactic discovery. And going to final conclusions on the key scientific results, we were able to discard that simple Barn models could explain the global phase space of the galactic disk. We point fairly strongly that dynamic dark matter spiral arms should exist, and they will increase this 10% of the mass of spiral arms, and they could have some implications on the direct detection of dark matter and the local distribution of dark matter. And again, we discovered that a single Sagittarius impact could explain this double wave pattern, and yeah, that's it. And just as a global conclusion of this thesis, a thing that has been recurring on this thesis is that we live in an era where we have these very good data sets of large simulations and a lot of data and coming surveys and coming simulations, and it feels somehow that these are growing every time apart from the pen and pencil first principle modeling that will explain us the physics of the problem. And I feel this thesis and this way of thinking and working is trying to build a bridge between these two things, and learn from simulations, but take these results and make them useful for first principle modeling. So that's it. Thank you.
So the committee is now moving to the table, I'm told, and we're going to ask questions to Marcel. Thank you very much for the very nice presentation. And I think I can ask Seska to start to open the discussion.
Yes, if you can, yes, perfect. So, Marcel, first of all, I have to say that I am impressed on the PhD thesis, but I'm impressed for the amount of work, but also for the quality of the work and also for the complexity of the work. Basically, in the last two chapters, my feeling is that you have opened, in some sense, a new line of research in the team, a new work to be done, a lot of work to be done, new techniques. I am impressed on Cindy, which are in fact the capabilities and the potential analysis. My questions will be basically on this new tool, let's say, as you said at the end, and also on the dark matter spirals that you analyzed. My first question, I go to chapter 5, I go to Cindy, I go in some sense to your slide number 34 or something like that. And also working on the paper, and also some slides, for example, 38. I have written, you are using Cindy, new technique, data driving, machine learning, how to derive the partial differential equations, how to try to solve. Very, very beautiful the fact that when something is linear or something is beautiful, you recover the Boltzmann equation, so it's very pedagogical, thanks for that. The question is when we are going to the nonlinear effects, that we are going there. When you are going to these nonlinear effects, you conclude in some sense in your work, you conclude that Cindy is missing important physics. This is one of the sentences you put in the thesis.
Mm-hmm.
You Cindy is missing important physics. But then, correctly, you use Gaia data, and in section 6, you try to work in this slide number, looking at that, slide number 38, looking at the, let's say, the application to our LZ, exactly, the LZ VR, mean VR plane. I saw that you cannot reproduce a two-wave. I see. You have used Gaia data, but even if you cannot reproduce the physics, you are saying that you can say, for example, due to the time since the impact of the Sagittarius, I recover 0.42 gigayears. That is something that is more or less reasonable. Mm-hmm. My first question here is, you use Gaia data, you try to apply this to Gaia data to have a paper on Gaia data also. But if you use, for example, the simulations of Tetsuro with the same technique you developed here, mm-hmm. which is and in a snapshot you will have imagined 500 million years after the perturber is coming. Will you recover exactly these 500 million years? Will be an ill-defined problem? Will have if you apply exactly your methodology, because the methodology in the paper, let's say, is in a footnote, but for me it's very hard to define which is the kind of mathematics you have in this footnote. Let me think like this. But the question is, have you checked it if when you use in a simulation like the one of Tetsuro you can?
So there are, I think there are two ways to go. No? When we use Cindy is we have the simulation that it's already done, and we use Cindy to discover how we got there. But when running it in Gaia in the Gaia data, we are doing the opposite. We are assuming that the model is already the output of Cindy, and then putting it on the beginning of the simulation and forward modeling it. The thing is, when we run Cindy in TensorFlow, we are doing it in the opposite way.
Yeah.
And what we find is that the fit is suboptimal. So the model that Cindy is giving back is suboptimal, and this suboptimality means that if we do forward model for TensorFlow, it will not work. It will return a simulation that is
like in Gaia.
exactly because of the missing terms that we were talking. We know that in Boltzmann equation, if there is a gravity, there must be the density term and the density gradient and all the intervals of density that would need to appear here, and we are not fitting them. So it's information that the model doesn't have.
And you will arrive to the same conclusion.
Yeah.
Then it goes to my second question with Cindy. You have done this 2D, let's say, but you have rings in R, in radius, independent rings in radius, right? Just to see how the coefficients apply and so on. Should be a next step, not working in this planar analysis, but going to the vertical analysis, like trying to do, for example, slices in Z, BZ or something like that. Do you expect to have something, let's say, a bit simple model that can explain the phase spiral and things like that?
I 100% think that you could extend it. I don't know how easy it is, because if you want to model the coupling, you go very fast to 6D formulation. You have to input 6D data, and then it's the equation grows a lot, and that's why we stopped at 2D and said that I think again it's a really good follow-up project, and I think that there is the capability.
And forced to the using a simultaneous zero. Phi equal to 0 and then go.
No. We forced to be okay. So doing
just
but then you are not picking the coupling. That is an interesting question. Yeah. No, the vertical physics, the isolated vertical physics are already fairly well done. So I guess the interesting scientific question is the coupling between the planar and the vertical. But
yeah. Okay. Complex and
yes.
Just opening this window to the analysis of the dynamics. This is something that I the other point that I was interested in is chapter 4. More questions. Okay. Chapter 4 is spiral arms. You, in some sense, you have this strong conclusion that does not matter the nature of the spirals. Can be tidal spirals. Can be that you recover that this forced response of the dark matter to the physical baryonic spiral arms in the galactic disk. And then in your paper, even in the abstract, you said that quantification. Okay, there is a 10% density of the dark matter. There is a lack of 10 degrees. Okay.
Yes.
I wonder about this, if this quantification is something robust or not. This is my point. Is this quantification robust? Because I have seen that you have been working with test particles, also with the Oakley simulations, with or without perturber. But again, for example, imagine if you take another simulation, that another initial conditions, another dispersions, do you expect to have these 10 degrees? Because should we look for these 10 degrees? Or these 10 degrees is so depending on the
two different things. First, the mass. No, we said it's 10% of mass. This is not a precise measurement. It will depend on a lot of things. And in the paper, we say that if the halo, for instance, is rotating in the same direction of the spiral, it will increase this percentage, and it will be maybe not 10, but it will be 15. But we know that it should be in a range between. I was asking the same question to Martin Weinberg at some point, and for the shadow bar and for the MC weight, it's very similar. It cannot be 100% physically, but it cannot be 0. So it has to be in a middle range, and that's why it's usually about between 5 and 20, but it's a approximate rule. As for the angle, it's kind of the same. And I will refer to Jason's last paper in the shadow bar. We see that if the it depends on the phase of the bar and the strength of the bar and the evolution. There is a different this phase difference is different with time, but it's always consistently in this 5 to 30 degrees range. So yeah, it's not robust, but it will always be on that order.
It comes to my question here, in the fact that I have followed the citations you have of this paper. And in the citation, it goes to the extragalactic, which is a very good point for us, that people coming from extragalactic is looking to your work, that it's good for this point of view. And they try to analyze this Renshaw rule that we were discussing this morning with that, in the sense that they compare how the luminosity rotation curve, let's say, matter, how the matter, the amount of matter will produce a rotation curve, blah, blah, and how this is dynamic rotation curve, which is the dynamics and that. And they think that there are some features that cannot be explained using maybe a mount or maybe that. My question here is, could this new approach to quantify the dark matter spirals that are being the response be in some sense, if you say 10 to 50%, be in some sense something that could explain these features that are not explained with this rule that every moment that you have something that as luminosity, you should be reflected in the rotation cube. Do you understand my question?
Yes.
Because I have seen in your paper, no? We can have the amount of distribution of mass, and we can have tal, but you have in the extragalactic something like that.
Yeah, this is a observation that has come up fairly recently, so I haven't read the paper in detail, but I think the way I understood this Rizzo-Renzo rule was that if you assume that the halo is much smoother than the disk, this smoothness should erase the features of the disk in the rotation curve. I think that the nice thing of this work is that it confirms that you will have non-smooth features that will always follow your non-smooth feature in the disk. So I think this helps, the citation helps refusing the hypothesis that this smooth feature will erase the other thing. Apart from that,
the question is the nature of dark matter. If you can say something in the future, if you can, in some sense, quantify.
Yeah. No, I think this is one way that I think that this could be used to test the nature of dark matter, and I think that's the second step. First step would be, can we say something about how this determines the growth of spirals? If this is closely related to the growth of spirals, then we can test, is this related to the growth of spirals in the same way if the dark matter nature is different? In a fuzzy dark matter scenario, this coupling works in the same way or not? Because then we get constraints. Observing spirals, we can constrain by a secondary, a second step using this tool. So yeah, I think it can be used, not in a straightforward way. I think it needs to be much more studied in the cold dark matter scenario, and then it has capabilities of moving it to the next step.
Okay, thank you. For the moment,
So I give the word to Jason.
Okay. This one first. Okay. Yeah, first of all, I just want to echo what Francesca said at the beginning. Really nice thesis, and it's very impressive to see what you've done. I'm also very excited about Cindy in particular, and kind of wish you'd done a little bit, another couple of years to see what we get out of it, but I'm excited to see whoever picks that up after you. So I had, in some ways, similar questions, but I'll just build a little bit. No, that's better, yeah. On one of them, for the vertical extension of Cindy, I agree it would be super exciting to do the full 3D, but also super difficult. But I wonder, could you get something out by just having, you know, the mid-plane mean vertical velocity wave? So you'd still be in a 2D, you run a full 3D simulation, then take a 2D velocity field and get out then propagation of the vertical corrugation wave that way without having to do the 3D equations.
That's an amazing approach. Yeah. And I think, again, no, and I think it's a very interesting project in the sense that the linear regime of that we know how works should propagate, or how analytic works propagate, and it's this omega minus kappa propagation. So I think it's lovely in the sense that we know that, and this nonlinear extension, maybe there is some kind of similar equation to that can be applied to the nonlinear regime of work operation. So yeah, I think it will be a very interesting project. Go for it.
Cool. And then, yeah, I also wanted to ask about the dark matter spirals. I had basically part of the same question on the nature of dark matter, but also, as we think at the moment, the enhancement level is somewhere around 10%. At the moment, we can't measure Milky Way spiral density to 10%, that's fine, but in the future, presumably, we will be able to. Do you have an idea of what future surveys or measurements we could make to start to tell the difference between that observed density enhancement and the kinematics that it's leaving in the stars to get out how much the dynamical mass would be, including the dark matter? Or is that still, you think, far too far away?
I mean, I think the methodology, the broad methodology, I think it's fairly obvious in the sense that you have stellar or baryonic mass, and then you have total mass, and you can ideally measure the baryonic mass by Gaia-Mir, for instance. That will give you a good measurement of the density. And then for the total mass, you have tools like Axel Widmark's potential measurement that can have this very high resolution measurement of the forces of the disk, and then subtracting one to the other. I think there's where this overdensity is. However, I think it's this 10% resolution error, and also there are signals that are one on top of the other. So it's extremely difficult to know if you are indeed finding this extra 10%, or it's just that you underestimated one of both. So I think it's feasible, but maybe with the lag. Maybe since there's this small lag, you could test if you see two lags over the still and blend them this way. Yeah. Cool.
Jumping back to Cindy for a second, for the LZ VR wave, you assume the impulsive perturbation and get the reasonable but imperfect fit to the wave and everything, and extracting the time of 420 million years. But that crossing, if it was the last one, would be far from impulsive because it's in the later regime where it sweeps under. So do you have any idea of how you can adapt the Cindy equations to account for non-impulsive perturbations, and do you think that would push that secondary wave in the right direction, or not? I don't know if there's intuition for that.
There's a fairly simple way to do it, that it's splitting the impact, or the orbit of the impact into a series of epsilon impacts, and then you can adapt all these different epsilons and this same setup, and you get results. This raises to question. We didn't, because then the parameter space again blows, but we tried at some point, and it did do good results. The question there is if this sum of small epsilons is still linear, or if this if you are still in the linear regime of and you can add those epsilons, or they are coupled in some unknown ways, and then you are yeah. So.
Yeah, do you want to do more of that?
We can.
Go back and, sure.
Yeah.
Yeah.
Okay, then it's it's my turn. Yeah, I also want to congratulate you on your thesis. It's been a pleasure to read and very impressive work. The breadth and the depth of it, and also it's very innovative. You're going in different directions, somewhat unexpected sometimes. So I had a couple of questions. Maybe we should round off the last chapters on the last chapters. So also on this one, I think in your conclusions, you said that that you can discard the origin of the double spiral as being due to Sagittarius.
Yeah.
And I find that a very strong statement. that it isn't actually warranted, because you don't actually you make a number of assumptions that actually are not. You could argue the system is 3D rather than 2D.
Yeah.
And in fact, Sag is going in the dimension in which you're not considering in your modeling.
I agree on that statement. I will also add to your point that when we go to this pointer, when we go to Tetsuro's simulation, this is an impact simulation, and there is no shortwave spiral appearing here. So this second spiral do not appear in general in simulation. So, and that's something we wanted to test with more detail that we couldn't because of time limitations basically. But we think that velocity dispersion, the first effect of velocity dispersion is that the amplitude of this second wave decays very fast. So that's why we are not seeing it. So I agree that there are a lot of limitations that would include that the initial setup is slightly biased, because we are inventing this second wave and discarding it in the same paper. So yeah, I think that there are ways that I think the way to go is try to find a model that fits these kind of simulations, the real ones, and then go to Gaia. We skipped that step, I think, in the paper.
Yeah, I think the other test that you could make is perhaps in a configuration, so because you're treating the problem two-dimensionally, but you know of the coupling in R and Z, and the motion of Sag is in Z.
Mm-hmm.
Is what would happen? Do you think this would actually work, or have you tried, if you had your perturber actually in the plane of the disk? Have you tried that?
If we are still in the distant impulsive approximation, the change of orbit is just a constant on the amplitude, and that is being entry main chapter X, and we tested in local simulations, and indeed, if it's far and distant, this angle change is just a constant. So for distant tidal impulsive, this will change the mass estimates that we get, but nothing else. So
But would you get the right mass estimate?
No.
No.
We
You think you don't?
Oh, we check the ranges. This factor is about a factor of 2, I think. So it's still in this 10 to the 10 regime. You will get 0.5 10 to the 10, but it's still like on the upper boundary of the mass estimates for Sagittarius.
Okay, so that actually brings me to the next question, which is your estimate of the mass of Sagittarius.
Yeah.
So I'm a bit puzzled, because I've done modeling of Sagittarius decades ago.
Yeah.
And a 10 to the 10 is not consistent with the current mass of the body of Sag, right?
Yeah.
In terms of stars.
Yeah.
So what happened since, I don't know, the year 2000 and 2025, and now it's a factor of 100 more mass?
I think I don't remember the phrasing exactly, but we were very carefully to not stress that we were giving a mass, or we tried to stress that we were not giving a mass estimate of Sagittarius. It was just this measurement is just a way to transform the initial amplitude, that is a dimensionless parameter, assuming distance of impact and a velocity, and then you get a mass estimate and you can compare. So I absolutely agree, and especially this could be consistent with the initial mass of Sagittarius before the stripping 6 gigayears ago, but not with the last impact. So I agree.
Okay, because you had a slide at the beginning where you said Sagittarius had 1/25 of the Milky Way mass.
Yeah, maybe that's a bad estimation. I don't know the numbers by heart of Sagittarius.
Okay.
Yeah.
Yes. Then I wanted to move also to the dark matter spirals chapter. So you have a plot showing, yes, yeah. So in this plot you get, we see a relatively good match in all velocities in the plane and in the density, but VZ is very different.
That's a good point. I wouldn't say it's very different. It's slightly different in the sense that here, the node here, I could see it going through the major density. I agree that it's slightly different. It also, again, the question of session. I think here we are using slightly lower pattern speed densities because that enhanced a bit our resolution for these simulations. We are here going to the limit of noise threshold, and I think this slight change of pattern speed could also bias how the particle response is. But yeah, again.
But do you understand why it's different in Z than what it is in the planes?
Why?
Yeah.
Here.
Yeah.
I think so. Let me correct. I'm not very sure of why it's positive in the plane. I could say my intuition says that it basically if you have the bar potential here and then you move it, and it's how the halo around it respond. So you could compute the vectors of these force vectors, and I'm fairly sure that the projection of those vectors would give this shape. It's a thing that I thought once the paper was published. I was like, we could have done this test. In terms of the vertical breathing motion, I think it's the same breathing motion as Victor is explained in their spiral arms paper, only that it's outside rotation, no? Because the halo is not rotating. So in this case, the arm always encounters the diameter particles in the leading part, and then it compresses in the leading, and then when the arm passes, it decompresses afterwards. So we expect this zero on the maximum density of the spiral potential. So I think we understand this very good. I think we could work an analytical way of this mass, but I haven't done it.
Okay, thank you. Yes, and then I was interested in a statement you made on the potential implications of these dark matter spirals, and I was wondering if you could elaborate a bit more on this. And also because I'm trying to understand, maybe you could mention something about if we know how much mass there is in the spiral arms.
Okay, I think there's one way to think about it, that it's what we discussed of the diameter nature, but the other thing I mentioned that I've not expanded is the direct detection setup. And we thought about this at the beginning of this project. The reason we didn't push in that direction is that, as far as I understand, what isn't interesting for this direct detection are high velocity subpopulations. It's a clear change of the velocity distribution of the particles. You have a fast halo or something like that. Or that's what we understood at the moment. And the thing is that when plotting the velocity distribution of these things, it's barely noticeable. It's a very thin change on the velocity, on the histogram of velocities. So we don't expect a second large populations to appear. So in that sense, that's why we didn't push strongly in that direction. What is true is that if we have an estimate of the local density of dark matter that is given by a homogeneous halo, if the sun is in an under density between two spirals, you expect a little bit less density than this homogeneous halo would give you. That's what we are claiming. But it's not a strong result that we can push out. I agree.
Okay. Okay. Then I guess we can, if you want to,
Just one question.
yeah.
Yeah.
First up.
Thank you. Last question. Maybe it's a crazy question, but
We like those.
no. My feeling was coming back to this response of the spirals. If we think that we have a thick disk, imagine a baryonic stellar thick disk or a dark matter thick disk if it exists, yes, not, etc. At this moment, do you expect from the stellar spirals in the thing that something, some luck, some spirals, something could be observed in the population of the thick disk that we can in some sense characterize by, let's say, the metallicity or let's say something. In another way, in your slide number 29, you analyze, I think very interestingly, this beta angle, exactly, this beta angle of the orbit respect to the plane. And in this moment, the thick disk population is just in the as the yellow.
Yeah. Yeah.
So which is your impression here? It's
So we actually tested something like that in the final editing of the paper, but it didn't go there because it was surprisingly difficult to do. But so the thing that we have in the paper and we conclude is, and following this, and we tested, we simulated it. If the dark matter halo is rotating somehow in the same direction as the disk, this coupling will increase, and it's almost linear. So as if the halo is rotating every time more, it increases. This coupling increases. So that if there is a dark matter rotating population, this coupling will increase. Also, if the halo is more flat, the local density of dark matter will also increase. So this dark matter spiral amplitude will also increase. And that's what we struggle because it's very difficult to flatten halos, maintaining the rest of the parameters constant. So we stopped doing that, but it will increase. The thing is that if a dark matter population flattens and starts to rotate, it ends up being a stellar-like population in the limit, and then self-rotating modes will appear, and we will have a different kind of spiral arms. So there's this balance of non-rotating halos with random distribution of orbits that will only respond, and then the thick disk that actually Judith is testing that right now at the moment, if the thick disk will produce self-rotating spirals or not. So there's this range in the middle.
okay, thank you.
I will jump back to your first year research chapter, so we ask you something on that as well. You did a really nice job of tracking the various ridges and kinematic overdensities and quantifying the gradients and everything, and in the end showed that it still doesn't match the simple Barn-Hauptl effect, so there's something else going on. So you have a nice illustration of all the other things that could be. I want to ask you more, how do you think we can break the degeneracy? What new data is needed? One other way of quantifying resonances is in actions instead of kinematics. Could you apply your wave level manifold finding to data in action space? Did you try that? Or if not, what future data do you think will be needed to break the degeneracy?
Yeah. Again, that was if we continued this project, the next logical step was let's find over densities in action space and go in that direction. In terms of how to break the degeneracies, I guess the first point of breaking the degeneracy is finding a model that properly fits the data and then move around that space to see how you can tweak that model and which parameters of the model keep you in the fitting model, and that's the problem, that we were not able to fit the model. So I think the first step will be, and again, in our to-do list, during this thesis, it has always been there, but things happen. But using a test particle simulation with a slowing down bar, can we fit this curve for even only if it's hat and Hercules? If we can fit those curves using this slowing down bar, then you can play with the parameters of the slowing down and say which is the range that you trust and which is the range that you discard and whatever. But first step is where we didn't got there. So yeah.
Thanks.
So I also wanted to ask a question about this slowing down bar, because you said there is consensus that it's slowing down.
Yeah.
So can you think of other ways in which you could test the slowdown of the bar? Any other way?
Any other, for instance, when I say there is consensus, I'm basically referring to one congress with Ralph Schumrich, very convinced that it was.
No,
He has a strong point. So that's sorry, it's online there. But in Rilke Shiva's paper, they use this Hercules trapping with metallicity, and the gradient of metallicity inside Hercules can also be an independent constraint of these bars going down. So yeah, there are different evidences pointing to that. So I think, again, it will be a very nice project to continue this.
Okay. And I have the chair's privilege to ask the very last one, which is one of the, I was intrigued by a statement you made on using Cindy for IFU data for external galaxies. Yeah. What do you think can be done there?
Again, on the question of that Cesca, the discussion with Cesca before, there are two ways you can think of Cindy. One is, with Cindy you always need temporal data, so you simulate, build a method, and then forward model. Where we think is, can we use this new fast simulating method that we obtained with Cindy to forward model the IFU data. And if we have velocity maps for IFU simulations, can we do this huge parameter search with these fast models to fit the IFU velocity maps? But yeah, of course, you cannot run Cindy on a fixed image because it's not designed to do that.
Okay, thank you. More questions? No? Okay, then thank you for this. I'm told that I should be asking if there is somebody in the audience with a PhD degree that would like to ask a question. No, I don't see any hands. Okay, then I think this closes the open part of this defense, and the committee will get together and discuss further. So thank you very much, and thank you, Marcel, for all your answers.
Thank you.